one problem, that is your u prime equal to minus 2t u square. Next, I think I have already promised on the last turn that I will tell various second order methods. So let me first share that slide and then I can talk about that. You might have seen it is already uploaded on this. I will just explain. Can you see the new slide? Can you see the new slide?
Yes, sir.
Okay. So there are some RK methods. First, we'll see this second order, and we I've written here that uj plus 1 equal to uj plus w1 k1 plus w2 k2. You have already seen that if it is an explicit method, then for second order we require this w1 and w2, and then two more, this a21 and a22. See, this all these things we require. So there are some various. So the notation is like that. Whatever is written here, it will be A21. Here it is C2. Here it is W1. Here it is W2. So for Euler-Cauchy method, C2 is 1, A21 is 1, and then your W1 and W2 are 1 by 2, 1 by 2. You might have seen that thing, right? And then Euler-Cauchy method, it was already told to you. And then modified Euler-Cauchy method is that we have that C2 as half, A21 as half, and then W1 is 0, only W2 is there, means only 1 is there, that is with your K2. And then optimal, you have already seen that C2 is 2 by 3, A21 is 2 by 3, and then 1 by 4 and 3 by 4 are your W1 and W2. So this is the optimal second order method. This is your modified Euler-Cauchy method, and the first one is your Euler-Cauchy method. So you can remember these easily. Otherwise, in the written form, it may be difficult for you to remember that. Then third order, I haven't done anything, but it is here that explicit, third order explicit. All these are I have taken directly from your book. It is copied directly from your book, that Iyengar book. Uj plus 1 equal to uj. W1 K1 plus W2 K2, you have already seen that up to this you can get only second order. So one more is taken, that W3 K3, and with that we get the second order, third order method. And then exactly the similar way your the notations are there. Whatever is written on this side, C2, C3, A21, A31, 32, everything is defined here. So W1, W2, W3. So accordingly, it is the classical third order method. Then nearly optimal, we cannot get the optimal one. Hohen method, and then Strom method. So all these are given. And then next is your fourth order method. Fourth order explicit method, I haven't told you before that. So as you see, I have already told that for implicit you have seen that we require only W1 K1, W2 K2, but for fourth order explicit method we require that W1 K1, W2 K2, W3 K3 and W4 K4. You have already seen that for second order we require W1 K1, W2 K2. For third order, we have to add one more W3K3, and then for fourth order, we have to add one more W4K4. Explicit method. And then it is given here. Things are quite simple as far as the classical fourth order method is concerned. Your C2 is half, A21 is half, and then your C3 is 1 by 2, and then A31 is 0, and then A32 is half, and similarly your C4, A14, A41, and then A42, A43, and then W1, W2, W3, W4. So in most of the cases, I can just tell you a bit of hint here. You will find that 1 plus 2 plus 3 plus 1. That is your 1 plus 2, that is 3 plus 2, 5 plus 1, 6 by 6, 1. Here also you can see that 1 plus 3 plus 3, this is again 8 by 8, 1, like that. So you may see this type of pattern. So you have to see that what type of pattern is there, and then accordingly. So some of this is your classical fourth order method. This you have to remember. So, and then your only Kutta fourth order method, Range is not there in this. Okay, so this is some simple thing which was left for this Range Kutta part.
Sir, in that multi-step method, so
Okay.
for the third lecture, in the second question, I have doubt.
Multi-step method. Which one?
Yes, a multi-step method. Lecture 3, third.
No, which method you have doubt?
Like
There
sir,
were Adam Bass. Wait. Adam Basford, then Adams Moulton, then Milne Simpson.
Sir, I understood the method, but say in one of the problem for the truncation error.
Okay. So where it was problem?
Yes, sir.
You can do one thing. You can share that. Do you have that file? It is uploaded here, or what is that?
Yes, it is uploaded. Sir, it is the third lecture 3, third problems on multi-step.
Wait. Problems on multi-step methods.
Yes, sir.
Okay. I think I have to come back to that, but little later. Okay, let me see what is your problem, then I will accordingly decide.
So the second example.
Wait. Let me share it, then you can tell me.
Yes, sir.
Second means that derive a fourth order method.
Yes, sir.
Oh, that I will tell you. Don't worry. That I will tell you. Maybe after some basic theoretical part, right? I will come back to this. Don't worry.
Okay, sir.
Because whatever the notations are used there, you are not. I mean, it is not told to you till now. Even though the file is there, but it is not told to you how the CIs are there and so on and so forth.
Yes, sir. That's what I was getting confused over there.
No, you cannot understand unless until I tell you. Okay, so that is the part I'm going to start basically.
Okay, sir.
Whatever I have told till now, that was the leftover part which otherwise I would have, I will forget once I will move further. Now, can you see the another slide?
Yes, sir.
Okay. So let me write the this multi-step method. Let me explain that notations for y prime equal to f. Obviously, as long as we are doing this initial value things, we are taking y prime equal to f with the initial value given, and the method is yn plus 1 equal to it is written in the summation form, otherwise it will take quite long. I have written in the middle, it is written in the expanded form also whenever it is required. So j equal to 0 to p. Obviously, I mean, all those things I have already told to you. You know it very well that if a problem is given, its domain is there, domain is given to you, then you have to subdivide that domain into subdivisions, and then suppose you divide in n number of subdivisions, then xn will be x naught plus nh, where x naught is the initial value, h is always greater than 0, that is your step size, very obvious. Now, with this, suppose we have the general multi-step method, which is written in this form. Sorry, as yn plus 1 equals j running from 0 to p, a j yn minus j. Don't worry. H times, this is the slope part, summation j running from minus 1. Keep this in mind. J running from minus 1 to p. If you put j equal to minus 1, this will be b minus 1, but here it will be f of okay, let me wait. I have forgotten to it is getting recorded. Fine. I forgot to start that. Anyway, so j equal to minus 1, it is b, coefficient is b minus 1. It's just a notation, does not matter. But here you see f of n plus 1, y n plus 1. Is that clear? If b equal to the first one, j equal to minus 1, this is b minus 1, f of n plus 1, y of n plus 1. Is this clear?
Yes, sir. Yes, sir.
Okay. So this is the term which is most important term. This is the implicit part. If b minus 1 is 0, then it will be explicit method. If b minus 1 is not equal to 0, this will be implicit method. Is that clear? Is that clear?
Yes, sir. Yes.
Okay, good. So, and then how many points are there? How many initial values are there, which you have to calculate? How many initial value you have to calculate?
Like from n minus j to n.
No, not like that. J running from 0. Here it is the below you see, it is written in expanded form. A naught yn for j equal to 0, a1 yn minus 1, right? And then ap n minus p. Is that clear?
Yes,
These
sir.
are the initial values which you have to get if you want to apply this multi-step method. Then these initial values you have to get from some other method. Is that right?
Yes, sir.
You have already seen this Adam-Basforth method, Adams-Moulton method, Milne-Simpson method. The only difference in Adam-Basforth, Adam-Basforth was explicit, the other two were implicit methods, right? Means that b minus 1 is 0 for your Adam Basforth, but for the other two, b minus 1 is not equal to 0. And the slope part also, it is written in the expanded form. I have written this b minus 1 separately because this is the most important term on which everything depends. Everything depends. Is that right? You have already seen that PC method also, that predictor corrector method. It was the coefficient of this fxn plus 1 yn plus 1 which had a major role to in the convergence of that PC method. Is that right?
Yes, sir.
Yes. Okay, so that's the reason it is written separately. So how many initial points, initial values you have to calculate? From n minus 0 to n minus p. How many? P plus 1.
P plus 1.
Right? Means what? This is a p plus 1 multi-step method. Means to get yn plus 1, you yn plus 1 is in the previous how many previous values? P plus 1 previous values. This method is in p plus 1 previous values. It means it is a p plus 1 step method. Is this clear? Is
Yes,
this
sir.
clear?
Yes.
Okay. Now you can understand which one is P. I mean 5 multi-step method, 6 multi-step method, and so on and so forth. Right? Now, there are certain notations which I have to tell you. Some of them have already been told. Actually, notations has already been told to you. The local truncation error is your y, if the method is given by that yn plus 1 equal to j equal to 0 to p aj minus aj yn minus j plus h, the slope part. So then tn plus 1 will be what? Error will be what? If I go back, error will be yn plus 1 minus the whole thing, right?
Yes, sir.
So this is what is written here. Tn plus 1 is yxn plus 1 minus all those things that j running from 0 to p, aj yn minus j, and plus h, j minus 1 to p, and then bj y prime. Either we write f or we write y prime xn minus j. And this is for n greater than or equal to p, otherwise this method will not work. Right? Because up to n minus p, these are the initial values.
Yes, sir.
Is that clear? Okay. Then this is also I have defined. What is tau n plus 1? I am writing 1 by h tn plus 1. So means this will give you the order of the method. This will give you the order of the method. So this tau h, which is taken as the maximum over all the points xp to b of magnitude of tau n plus 1 y, that is this thing, means it is the maximum of that order of the methods, and that will definitely depend on h. You understand that if h approaches to 0, this goes to 0, then method is convergent. Then the method is convergent. Is that right?
Yes, sir.
Okay. This is the major part, and this is called basically tau h goes to 0 as h approaches to 0 is called the consistency condition. It is called the consistency condition. So any method which you develop should be or must be consistent. Must be consistent. Otherwise, if it is inconsistent, means you are getting something else at one stage, and if you apply again, then you, I mean, with this another initial guess, you are getting something else. So it has to be consistent. It has to be consistent. Means if h is very, what is the meaning of h approaches to 0? If h is very small, then the error is very small. The error very small. In that case, we say that method is consistent. Method is consistent. And if tau h is of order for the largest value of m is of capital order s to power m, then we say the method is of order m. So there are two things. One is your local truncation error, another is your order of the method. Local truncation error is order of the method is 1 by h, and then take the magnitude times your local truncation error will be your order of the method, right? Now we'll see some two theorems, two basic theorems. I'm not going to give the proof of that, it is not in your course, but even the proof is given here. This proof is done in your that book, that Atkinson book. If anybody is interested can see, but it is written here also, one can see the book also, but it is not in your course. Now let us see. So the notations, you understand that tau h is the maximum of 1 by h tnh, tn plus means local truncation error, and then maximum of that is taken as the tau h. So for m greater than or equal to 1, in order that tau h goes to 0, as h approaches to 0, holds for all, this is the theorem, holds for all continuously differentiable, because y prime is there, so continuously differentiable yx, that is the method, that is your general multi-step method which I have written, be consistent. It is necessary and sufficient that summation j running from 0 to p aj equal to 1, and then minus summation j running from p j aj plus j running from minus 1 to p bj equal to 1, right? This is the theorem. And the you see from where these things are coming, they are not falling from somewhere. It is exactly the same way what we have done for the Range. That's the reason I have explained your Range-Kutta method in a different way, so that you can understand each and everything. If somebody wants to see the proof, you will see that there also yn plus 1 is written in terms of yn. All the yn minus j's were written in terms of yns. These y prime n minus j's, they also have been written in terms of yn, and then the coefficient of h square, all those things were collected and they were made to 0, up to, depending on up to what order method we can get from that, right? Exactly the same way the proof of this theorem goes actually. And then for our the method should be of order m, our tau h is of capital order s to power m, be valid for all functions yx and rm plus 1 continuously differentiable. It is necessary and sufficient condition that 8 holds. 8 holds means first thing, it should be consistent. First thing, the method should be consistent. The second part is that order of the method, means along with that, that has to be satisfied, 8 has to be satisfied, and then further it has to satisfy this equation, that is summation j running from 0 to p minus j to power I a j plus I times summation j running from minus 1 to p minus j to power I minus 1 bj. This must be equal to 1, right? So these two conditions are there. So either you remember this, or you just simply write down the Taylor expansion and proceed further. Now, the problem which you raised, that Sneh Bandhu, I will explain later on. So whether this theorem is clear or not? Whether
Yes.
this theorem is clear to everybody?
Yes, sir.
So two things are there. One, consistency. Every method has to be consistent. Means that equation 8 has to be satisfied. Second, if it is of order m, then what should be the condition? So along with that 8, you further require that equation 9, right? Okay, so next theorem, which I have hinted during the theory part or the once I was developing the methods. This is the second theorem. Now, either you say the speed or you say the order of the method or the speed of the method. Both the things are same. Now, let us consider the initial value problem y prime equal to f with the initial value given. The domain is your x0 to b, and the general multi-step method I have already written here. Let us take that since we are getting that p plus 1 initial values using some other method, and let us see that let us take that the local truncation error for those initial values is your eta h, which is your maximum of magnitude of yxi minus yi, and this goes to 0 as h approaches to 0. Further, assume that the method is consistent, that is, it satisfies that tau h goes to 0, that first condition, and finally assume that the coefficient aj's are non-negative, that is, aj's are greater than or equal to 0 for j running from 0, 1 to p. Then the method 1 is convergent and maximum of yxn minus yn is less than or equal to C1 eta h, C2, these are two constants, C2 tau h. Eta h is the local truncation error. Let me explain this. Eta h is the local truncation error for the initial values. Tau h is the order of the method for your remaining values from yp plus that was j equal to 0 p plus 1 onward, right? Now here tau h means what? Tau h means 1 by h times local truncation error. Is that right or not?
Yes, sir.
Yes, sir. This is so I want your respond basically continuously. Tau h is order of the method, means h times tau h if we write, that will be what? Local truncation error for what?
For like our expression yn plus 1.
No. For no, must understand there are two parts. One part is initial values, that is y0 to p, y0 to yp, and then using this multi-step method we get yp plus 1 onward. Is that right or not?
Yes, sir.
Yes. Now you see y up to yp we are calculating through some other method. y0 to yp, these are the initial values you have already seen in Adam-Weisforth method. For example, of third order, you have seen that you have to calculate your y1 by Taylor's method or some RK method or anything of that kind. So their initial values are calculated through some other method. So they have some other local truncation error, and this tau h times tau h, I'm not saying tau h now, I'm saying h times tau h will give you that the local truncation error for the values which you have got using this multi-step method. Is that right?
Yes, sir.
Okay, this has to be clear. Otherwise there will be trouble. If anybody has any trouble at this stage, you ask me, because next thing what I am going to tell you, this on the left hand side, it is from x0 to b, means the maximum of local truncation error of all the values, is that right? Is that
Yes,
right?
sir. Yes, sir.
On the right hand side, this will be almost same as the local truncation error for initial values that is y0 to yp, and order of the method of those values, that is your ypp plus 1 onward, yp plus 1 onward. So if you want, suppose we want that this should be of order m, that maximum of yn means the total error which we local truncation error, we want if it is of order m. If it is of order m, means eta h should also be of order m, tau h should also be of order m. Right?
Yes, sir.
What is the meaning of eta h of order m? Eta h equal to of order m. Local truncation error for initial values
So, sir, for
should be of order m, s to power m. Right?
Yes, sir.
What is the meaning of this? In other words, in terms of the order of the method which you have applied for initial values, it will be one less, because you have to
Yes.
do for order of the method, you have to divide by h.
Yes, sir.
So with the order of the method for the initial values is m minus 1, right? While what is the meaning of tau h equal to of s to power m? Means its order is of m. Order is m. So if we want order m final error, then we should have one less order for the initial values. This is what I have told in the beginning also, that it seems that we should at least take, suppose the second order multi-step method is there, then the initial values should be calculated at least second order method. But in fact, we can work with the one less order, that is order 1 method for the initial values, and second order multi-step method which we have. With that, we get the final order will be of order second order. So means first order method for initial values and second order multi-step method for your other values finally will give you the second order method for your total overall error, total method. Is that right?
Yes, sir.
It is mentioned, it is written also here, it is written order m, so it will be m plus 1. Local truncation error has to be of order m. So it is whatever I am saying is written here also. Meaning by that, if you want to apply any order, let us say fifth order method, fifth order multi-step method, then remaining the initial values you can calculate by a fourth order method. With that fourth order method itself, you get the final order will be your fifth order. So one less order of the initial value calculation, we can get the higher order multi-step method. Is that clear or not?
Yes, sir.
So you just read this paragraph again and again. Then if anything is not clear, that will be clear. If anything is further not clear, you can ask me on the next one. The proof of this theorem is also not there. So even though the proof is written here, if you want, you can see that some basic analysis is used, nothing else is used. So these two theorems are very, very important. Now, we'll use this first theorem, the problem you were talking about. So I will explain by two methods that problem. I'm just showing you. Let me close this slide and then come back to that another slide. Can you see this slide?
Yes, sir.
Okay. This was the problem.
Yes, sir.
I think I have to just tell you a bit of things, and then from where the C naught and all those things are coming. In this problem, it is written as, let me. The problem is like, I think this problem is given in your book also, that in the exercise part, it is given, if I remember it correctly. Derive a fourth order method of the form yn plus 1 equal to a into yn minus 1 plus h into this way it is written yn prime c into yn minus 1 prime, d into yn minus 2 prime, e into yn minus 3 prime. Right now, there are two. So let me first write tn plus 1 will be yn plus 1 minus the whole thing. So it is taken on the other side. This is your yn plus 1 minus all the things which I have written with the minus 1. Is this clear, Snehabandhu?
Yes, sir.
Okay. Next thing, C naught is the coefficient of constant term. See here, if it is equal to C naught yxn, everything you have to write in terms of yxn. Everything means you have to write down the Taylor expansion of yxn plus 1, that is your yxn plus h times y prime xn, and so on and so forth. Is that right?
Yes, sir.
Next, yxn minus 2 also you have to write down in your yxn, means yxn minus 2 will be, it will be xn minus 2 means what? Xn minus 2h.
Yes, sir.
Xn minus 2h. So that will be your yxn minus 2h times y prime xn, and you write all the complete all the terms of the Taylor series, right?
Yes, sir.
Similarly, you write down for y prime xn minus 1. So y prime xn minus 1 Taylor expansion will be y y prime xn minus 1 minus h times y double prime xn minus 1, xn, then sorry, y prime xn minus h times y double prime xn, and like that. So write down all the Taylor expansion. Similarly, for y prime xn minus 2 means y prime xn minus 2h times y double prime xn, and other terms. Is that clear?
Yes, sir.
Then similarly you have to write for y prime xn minus 3. means it is xn minus 3h. Right?
Yes, sir.
Now, since you have to see what order it will be, so you cannot truncate at very early stage. You may go up to 5th and 6th term. No, it is written as derive a 4th order method. Means what? What will be the order of the local truncation error?
5.
5. So capital order s to power 5 term, you need not to write. Means for yn plus 1, you have to write up to capital order s to power 4 term, and then s to power 5 will go to the local truncation error. Similarly, yn minus 2, you have to write up to order s to power 4 term, and order s to power 5 will go to the error term. Here you h into those things are there, the slope part. Here you have to write one less order, means up to order h cube, and
Yes.
h to power 4 part will go to local truncation error. Is that clear?
Yes, and now I got it.
No, wait. And then C naught yxn, C naught is the coefficient of yxn, C1 is the coefficient of h into y prime xn, C2 is the coefficient of h squared times that, and C3 like that, C4, C5, and so on and so forth. Is that clear? Now, you compare the coefficients. So constant term, what you have got in that theorem, the first term, first condition, that is your this C naught, the constant term. C1 was the second one. So this C naught and C1, they are necessary for consistency. So they have to be there. Then further for the order of the methods, C2, C3, if you see the proof of that theorem, you will immediately realize that how it is coming. C3, C4 and all those things are there, and then all these should be equal to 0 up to C4, because up to C4 it has to be 0. Did you understand why? If up to C4 it is 0, then the local truncation error will be only C5 s to power 5 and then y5 or whatever it is there. So this will be of capital order s to power 5, means the method will be of 4th order. The method will be of 4th order. To get the 4th order method, the C0 should be 0, C1 should be 0, C2 should be 0, C3 should be 0, and C4 should be 0. Is that clear?
Yes, sir.
Adrija? Adrija?
Yes.
Are you there?
Yes.
So
Yes.
whether I will explain further, I will explain this method. So if you use those equation 8 and 9, then you will get C0, C1. You can verify this. Maybe I have something somewhere. I will show you. So you can find this C0 now, C1, C2. You can write down the expansion, see whether it is coming the same thing or not. There might be here in C4 there is one error. You note down this. In C4, you please note down that it is 1 by 24, 1 minus 16a, I think. Let me check it. I will tell you. On page number 3, C4 is there. Snehamandu?
Yes, sir.
So this will be your 1 minus, let me check where it is. Yeah, it is 1 minus 16a. So make this correction. Have we written that correction?
Yes, sir.
And then by solving these equations, you will get that A is 1, B is this, and C is this, D is this, E is this. Right? This is one way. This is one way. And then I will, shall I close this? Shall I close this slide?
Yes, sir.
Okay, I will show you another one, another way. I think the another way is there. Let me check it. You are able to see the slide, new slide?
Yes, sir.
Yes. Now look at that first. Everybody, look at that. I have just rewritten that theorem, the major part, the multi-step method, then your the consistency condition, then your order of the method. This was the equation 8. This is the equation 9. Just see that. Do you understand?
Yes, sir.
So what are these AIs and BJs? AJs and BJs? That was in terms of ABCD. The method was, you just write down the method. Method was given to you. Since otherwise again I have to go back to that. Write down. Yn plus 1 equal to a times yn minus 2. Have you written?
Yes, sir.
Yes. So, and then next term is with h, that slope part. So here for first part, summation j running from 0 to p, only one term is there. That is your a into yn minus 2. And here the equation is what? J equal to j running from 0 to p, yj, aj equal to 1. Right? Right?
Yes, sir.
What should be a equal to 1? Here only one term is there. That is a into yn minus 2. So 1 minus a or a equal to 1, whatever you call it. These equations give, because in the equation, it is your, you write down the complete equation. I'm just dictating you. Write down yn plus 1. Otherwise, I have to open that slide again. Yn plus 1 equal to a into yn minus 2 plus h inside the bracket b yn prime plus c yn minus 1 prime plus d yn minus 2 prime plus e yn minus 3 prime. Right?
Yes, sir.
Have you written that? Okay.
Yes.
So with the slope part, there are 1, B, C, D, and E. But with the other one, it is your only one term. That is your A into yn minus 2. So the first says that j running from 0 to p, aj means all these things for this coefficient. Remove this yn minus j. But here only one term is there, that is a. So a equal to 1. So that is your first equation. See here. Right? Is this
Yes,
clear?
sir. Yes, sir. Yes, sir.
Okay. Then next is What is the next equation? -1 j running from 0 to p j into aj plus j running from -1 to p bj equal to 1. So what will be this one? It is your a into yn minus 2. So that will correspond to what? Minus is outside that. So minus n minus 2 means 2 times a. J times a means it corresponds to what? Which value? Here it is n minus 2. Where it will come? In a2 or j equal to 2. Is that right?
Yes, sir.
So that's the reason it is j into aj means 2 times a minus 2 times a. Right?
Yes, sir.
Plus with the slope part j running from -1 to p all the terms. What are the terms? Here with h part it is your b, the coefficients are b, c, d and e. So do that sum. So b plus c plus d plus e. See here it is written. So minus 2a plus b plus c plus d plus e equal to 1. Right? So this
Yes.
gives you second equation. Now, I mean, once I have first method, I have told that you write down the Taylor expansion, collect the coefficients of powers of h, starting with your h s to power 0, and then make that to 0. Second method, apply the theorem. Both way you will get the same thing. Apply the theorem. So first two conditions I have told you. Is that clear?
Yes, sir.
Then shall I leave the other conditions? For I equal to 2, you have to use this one, this equation, that summation j running from 0 to p minus j to power I is 2, so this will be squared, so it is plus. So j running from 0 to p aj plus I means 2 times j running from -1 to p minus j to power I minus 1, that is only minus j, and then bj. Bj's are known to you. Is that right?
So for I, we will go up to the order, right, sir?
So that's right, up to the order. Order
Okay.
is 4. So for I equal to 2, you will go. For I equal to 3, you will go. And for I equal to 4, you will go. All the equations are written here. This is the some name of file is supplementary problem on multi-step method. The last file it is there. So there it is done through another through using the theorem. Is that clear now?
Yes, sir.
Snehabandhu? So
Yes,
now
sir.
it is done through both the ways. It is up to you which way you adopt.
This
Right?
is the easiest one.
This is the,
Easiest one.
it may be easiest one, but the trouble is that you have to remember the formula.
Yes, sir.
Right? So it is, that's the reason I said it is up to you which way you want to do the problem. So I have told both the ways. So is this part clear?
Yes, sir.
Okay. Adrija?
Yes, sir.
Things are clear or not? Yes, Adrija?
Sir, I'm having network issues. Am I audible?
Yeah, you are audible. You are always audible to me. I don't know why you have the network issue. So you should do at least one thing, that Adrija, don't mute yourself. You can go through the notes, and in case you have any trouble, then you can ask me. Sajid
Sure, sir.
Ansari?
Yes, sir. So
Sajid
shall I mail you
Ansari?
if I have doubts?
No, you can ask me. Your voice is coming to me very clearly. Right?
Okay, sir.
Sajid Ansari, are we there? Rishabh Agarwal? Rishabh Agarwal? Aditya? Aditya Jha?
Yes,
There are
sir.
two Aditya. You are there. Okay.
Yes, sir. Present, sir.
Then another Aditya is there. Aditya Chawla is also there. There are
Yes, sir,
several
I am
Aditya. Aditya Agarwal is there.
Yes, sir, I'm there.
You are there. Okay, good. So whether you are able to understand? Are you able to understand? Anurag Singh?
Yes, sir.
Anurag Singh, you are
Yes,
there.
sir.
So whether you are able to understand?
Yes, sir.
Sure. Your voice is not telling that you actually understand.
Sir, actually, I missed a couple of classes, so I'm facing some trouble, but I'm trying.
But everything is there. All the class notes, videos, everything is there, right? The only
Yes,
thing
sir.
you have to take the pen and try to sit down and do something. Otherwise, there will be lot of method. I have already told that plenty of methods will come in the picture. Ayush Surana? Ayush Surana? So, to whomever I am calling, their attendance will be deleted. Yashvi Jain? Yashvi Jain? Okay, fine. Kavita?
Yes, sir.
You are there. Okay,
Yes, sir.
good. So, you are able to understand?
Yes, sir.
Naman Goel? Naman
Yes,
Goel?
sir.
So, you are there.
Yes, sir. Yes, sir.
Sir, you called me.
So, you are able to understand or not?
Yes, sir.
Everything is yes, sir.
Sir, I'll try it. I'll try it after
Huh?
the class once myself. I will try it after the class also once.
Not for today's class, I am telling. I have already taught lot of things.
Yes, sir. Earlier, once are clear this example, I'll try it once.
No, this example you can try. I have already told two methods, right? So you can see by any of these methods. Okay, the next
Okay,
thing I will move further. That is the stability part of the single step method first, and then I will go to the multi-step method. Yashvi Jain? Yashvi? You want to say something? Yashvi? Don't send that. Do you want to say something? Yashvi? You have any mic problem? Okay, I will move further. As I have already told, wait. I think I haven't shared. Let me share it first. Now, can you see this slide?
Yes, sir.
Okay, good. So, we have already seen while talking about this PC method that we have taken the differential equation to check the convergence y prime u prime. I think I don't remember either y prime or u prime equal to lambda u, and I have already said that this is called the test function, right? So this is what is written that u prime equal to lambda u is called u prime equal to lambda u is called the test function. Now we are solving this problem, y prime equal to f. Is that right? Whatever the method we are applying. Is that right?
Yes, sir.
What is its exact solution? Let me see that first. So u prime if the problem is your u prime equal to lambda u, so this will be u prime by u equal to lambda, or du by u equal to lambda, and then integrate that, you get the solution. Its exact solution will be analytical solution, rather I say, will be your u equal to some constant, let us say eta naught, that is your ut naught is given as eta naught into e to power lambda t. Is this clear? This you have done in your first year, even maybe before coming to this place, right? This will be the exact solution.
Yes, sir.
Okay. Now, so utj plus 1, if at the point tj plus 1 we see eta naught e to power lambda tj plus 1, and utj will be eta naught e to power lambda tj. Divide these two, means utj by tj plus 1 divided by utj. So this will be your e times lambda, sorry, exponential to power lambda, and then tj plus 1 minus tj, that is the step length, that is your h. So it is your e to power lambda h, or we can say that u tj plus 1 equal to e lambda h u tj. Is that correct?
Yes, sir.
Is that correct?
Yes, sir.
Okay. Now, before explaining the remaining part, I will just come back to the Euler method. This is Euler method is written uj plus 1 equal to uj plus h times f. Here the problem is u prime equal to lambda u. So what will be this? Uj plus f is your lambda u. So it is h lambda uj, right? So it will be your inside the bracket 1 plus lambda h uj. We can write like this.
Yes, sir.
Yes. Okay. Now let us see that Taylor's method of second order. This is your uj plus 1 equal to uj plus h uj prime plus h square by 2 factorial uj double prime. Right? U prime is f. So u double prime will be du by d by dx of u prime. So that is your lambda u. So it will be your lambda into lambda of lambda u prime, that is lambda into lambda of u, that is your lambda square u, right? So u double prime will be lambda square u. Similarly, you can check that for this f, u triple prime is lambda cube u, right? Put everything back into this. So this will become uj plus 1 equal to 1 plus lambda h, and then lambda h square by 2 factorial uj, right? Is that right?
Yes, sir.
And what you have got for the exact solution, it was u tj plus 1 utj plus 1 equal to e to power lambda h utj, right? This
Yes,
was the
sir.
exact one. This was the for the analytical solution, which is the exact one, right? Is that right?
Yes, sir.
Now, instead of e to power lambda h, here what is that you have? For the numerical method, uj plus 1 equal to something, let us write e, capital E lambda h into uj. Some approximation to e to power lambda h. Is this approximation to e to power lambda h or not? Either we write 1 plus lambda h, or we write 1 plus lambda h plus lambda square h square by 2. So up to first term for e to power lambda h, this is the approximation. Up to second term, second order term, it will be this approximation. Yes or no?
Yes, sir.
Okay, so now I can write like this. So any numerical method, you can see that can be obtained by writing the approximation to e to power lambda t, say e to power lambda h as 1 plus lambda h. This is your Euler method. E to power lambda h, if it is this is the sign for the approximate one. So e to power lambda h as 1 plus lambda h plus lambda square h square by 2. You may see some of the third order method can be written in this form with by taking that approximation to e to power lambda h, the way I have written for Euler and Taylor method. Exactly that way you can see that 1 plus 1 plus lambda h plus lambda square h square by 2 plus lambda cube h cube by 6 or 3 factorial you can say. Similarly, fourth order method you may get these type of things. So the numerical methods can be obtained by writing some kind of approximation to e to power lambda h, and we will get. So if you write this approximation, means you have the local truncation error there, that is your remainder term, and that will go to the local truncation error part of your numerical method. So any numerical method we can write the way we have got this for exact analytical solution, that utj plus 1 equal to e to power lambda h utj. We can write the numerical method as uj plus 1 equal to e lambda h, I am writing here the notation, into uj, where e lambda h is some kind of approximation to e to power lambda h. Is that part clear?
Yes, sir.
Okay. Then for numerical method means what? What we do for numerical method? We ignore the local truncation error by deleting the local truncation error. Whatever is written, that will be your method. Means a exact solution utj plus 1 will be e lambda h utj numerical solution plus local truncation error at that stage. That is your tj. Right? So this will give you exact. So and the exact solution will satisfy this equation 6. Is this clear?
Yes, sir.
Okay. Let us write epsilon j. That is your error part. Epsilon j as uj numerical value minus utj, that is exact value. Or we can write uj as epsilon j plus utj, whichever way you want to write. Wherever it is required, whichever way we'll use that. Now, so here it is in equation 6 on the left hand side, utj plus 1 is there. We'll rewrite this. This is your epsilon j plus 1 plus utj plus 1. I mean, basically from 5 if we see. So it will be your epsilon j plus 1 plus utj plus 1. If you put in this 5, if you see this from 5, so it will be your epsilon j plus 1 plus utj, that is your where it is written. I have written somewhere here. Uj is your epsilon j plus your utj. So epsilon j plus 1 plus utj. Epsilon j plus 1 plus utj plus 1 will be your uj plus 1, right? And then this is your e lambda h, and then utj. Utj is written epsilon j plus utj. So I have just put this one. this value here. So, so here, I mean in 5. So it will be your epsilon j plus 1. I will take one side, remaining other things I have taken on the other side. This is taken from your book, but certain things may not be explained very clearly. So epsilon j plus 1, if you rewrite this, it will be your minus utj plus 1 plus remaining term e lambda h epsilon j plus e lambda h utj. And then from 3 utj plus 1, as I have you have already seen for your exact one, e lambda h utj. So put that value. So epsilon j plus 1 equal to, this is written here, e lambda h utj, and then all the values are put here. It is rewritten. Utj part is taken together, epsilon j part is taken together. So we get that e lambda h minus e to power lambda h into utj. This e to power lambda h comes from your exact solution. E lambda h comes from your numerical solution. So that's the reason the word is used here. It is local truncation error, the truncation error. This is what the approximation you have taken for e lambda h to get some numerical method. So this is called the truncation error, along with utj obviously. And this part, e lambda h into epsilon j, this is the error committed at the jth stage. This is the error committed at the jth stage, which comes at j plus 1 at this stage also. That's the reason. And then whatever the error you commit at j plus 1 at this stage will go to j plus second stage, the second iterate value. So this is called the propagation of the error. Is this part clear? So this is your truncation error, and this is your progression of the error. This propagates at every stage. Is that clear?
Yes, sir.
Okay. So we'll just try to see how this propagates at next stage, j plus 2th stage. Whether it is power, its power, e to power lambda, e lambda h power, or something is multiplied there or something is added there. What is happening to that? So we'll just try to see at j plus second stage. So epsilon j plus 1, sorry, j plus 2 will be this quantity into utj plus 1. Instead of tj, it will be tj plus 1, and e lambda h epsilon j plus 1. We'll put these values, epsilon j plus 1 in terms of epsilon j. So epsilon j plus 1 can be written as e lambda h minus e to power lambda h into utj. So you just multiply, you simplify this. Finally, you can see that we are getting that at j plus second stage, epsilon j plus 2, the error at this j plus second stage or state, what is happening? This is coming as e square lambda h minus e to power 2 lambda h and utj plus e square lambda h epsilon j, means it becomes square at the second stage, epsilon j plus 2 if it is j plus second stage. So whatever the error we have committed at epsilon jth stage, it becomes a square of that. In e it becomes a square. Then if you want that epsilon j plus kth stage, what is going to happen? You can write it directly. Just the way we have proceeded for j plus 1 to, okay, there are one or two things which we have written here that I will just go back a little bit. This term we have already told as truncation error, because earlier you have seen only e lambda h minus e to power lambda h. Here it is e square. So whether it is the local truncation error or not at this stage. So this is what is justified here. Utj plus 1 equal to e lambda e to power lambda h utj. Utj plus 2 is your e to power lambda h utj plus 1. or we may write this as, again you write utj plus 1 as e lambda h and then utj. So the e to power lambda h, e to power lambda h, that will be e to power 2 lambda h into utj. So utj plus 2 can be written, the exact one can be written as e to power 2 lambda h utj. Is that right? Is that right?
Yes, sir.
And then for numerical, you write e lambda h instead of e to power lambda h. So uj plus 1 equal to e lambda h uj. Then uj plus 2 will be e lambda h uj plus 1. Put the value of uj plus 1. So this becomes e square lambda h uj. So corresponding to this means the e square lambda h minus e to power 2 lambda h is nothing but the local truncation error for that j plus second stage. So that's the reason this word is used, local truncation error. So for kth stage, that epsilon j plus k, the error committed at jth stage will be propagated as follows: e to power k lambda h epsilon j. Whether up to this things are clear?
Yes, sir.
Now here you have to understand, if you can stop the propagation error, because you are committing some error at jth stage which is getting propagated at every further stages. This is what is happening, right? So if you can stop, you can make this error to zero, this propagation error, then the method is fine. If this blows up, this error, propagation error blows up, means your method is not at all stable, right? Is this point clear?
Yes, sir.
Now that is the point. So when this will be in your control, when this is power k is there, when magnitude of e lambda h is strictly less than
1.
1, then your propagation error will be in your control and you can control it. So means that this method will be stable. This method will be stable. So now at this stage, we can define certain things. That is, a method is stable if cumulative effect of all the errors. This includes your round off error that is not in your control, depends on which machine you are working, and then your local truncation errors, all the errors. If a method is stable, if cumulative effect of all these errors is bounded independent of mesh division, right? This will be independent of mesh division only when you have h is very, very small. Is that right? Then it does not matter if the method is stable. Is that clear?
Yes, sir.
Okay. Absolutely stable if magnitude of e lambda h is strictly less than 1 for lambda less than 0. It is not working, this PDF property here. Here it is in the note it is written lambda less than 0. If it is true for lambda less than 0, then only we will say that it is absolutely stable. So make that correction. Then relatively stable. If you open the file outside this MS Team, then you can read this note without any trouble. So relatively stable means e lambda h, exact solution is having e lambda e to power lambda h. So if e lambda h is strictly less than e lambda h, means it is comparable to your e lambda h. For lambda greater than 0, here it is greater than 0 is there for the note 1, then the method is called relatively stable. Then the method is called relatively stable. If it is less than e to power lambda h, e lambda h, that approximation, then the method is relatively stable. Is this clear?
Yes, sir.
Is this clear? Okay, so let me see at least one example. That is your Euler method. Euler method, we have already seen that e lambda h is 1 plus lambda h, right? I have already told in the beginning itself.
Yes,
it is
sir.
strictly less than e to power lambda h for lambda greater than 0. You can say that because the e to power lambda h has 1 plus lambda h plus lambda square h square and by 2 and so on and so forth, right? So it is always 1 e lambda h is always strictly less than e to power lambda h for lambda greater than 0. So it is always relative stable. It is always relative stable. When it will be absolute stable, for lambda, for absolute stability, you require lambda should be less than 0. So means 1 plus lambda h should be, e lambda h should be strictly less than 1, meaning by 1 plus lambda h should be strictly less than 1. Or we can say 1 plus lambda h is greater than minus 1 and 1, or lambda h is greater than minus 2 to 0. So the stability region will be 0. Why 0? Why we are not going from 0 to 1? Because we want lambda should be less than 0. This should be true for lambda less than 0 only, then we'll say. So 0 to 1 will not be counted. The intersection of this with your left half part of lambda plane. So that will be your minus lambda h is greater than minus 2, but it is only up to 0. Means if lambda h is in minus 2, open minus 2, 0, then the method is absolutely stable. Is this clear? This is called the interval of stability. This interval is called the interval of stability. Is this clear? Is this clear to everybody?
Yes, sir.
Okay. The second one, the second Taylor's method of second order. You have already seen that e lambda h is 1 plus lambda h plus lambda square h square by 2. Again, you can see very clearly that for lambda greater than 0, e lambda h will always be strictly less than e to power lambda h, because further you have plus lambda cube h cube by 3 factorial and so on and so forth. So this is always for lambda greater than 0. What will happen for lambda less than 0? Can you quickly tell me? This is simple inequality. You require that for absolute stability, you require lambda, for lambda less than 0, magnitude of e lambda h should be less than 1. So 1 plus lambda h plus lambda square h square by 2 should be, magnitude of this should be less than 1. So what will be the condition on lambda h? What will be the region for stability or the interval of stability? Tell me quickly. You can do that, all of you. Do you understand what I have asked?
Yes, sir.
Okay, do it quickly. Tell me. Quickly tell me. Should not take much time. Anybody?
We have to make perfect.
Pardon me?
So we have to make perfect.
Check it. I have done that, something like that, perfect type of thing. But there are several ways to do that, not one way. Okay, let me show that. This is less. You may write this as 1 by 2. You can take out 1 plus lambda h whole square. You can write, because 1 by 2, if you take out, this will be lambda square h square plus 2 lambda h plus 2. So I will write this 1 plus 1. 1 I will take with this. So that will be 1 plus lambda h square plus 1. Is that right?
Yes, sir.
Is less
Yes.
than 1. Yes? Anybody?
Minus 2 to 0, sir.
Exactly. it will come from lambda h should be strictly greater than -2 and less than 0. Now, up to second order, there is no trouble. But if E lambda is third order, fourth order, fifth order, then it is not possible to use this simple 10th standard technique. It is very difficult to solve a cubic equation or 4th degree or 5th degree equation, right?
Yes, sir.
Then another option is that you see the graph of that. You see the graph of that by putting certain values of lambda h, see what is happening. So for example, this third order method, if it is there, and we can see that at lambda h point minus 0.25, the value is minus 0.979. If we exceed a bit, then it will increase to it will go to the positive side. One may do that to minus 2.501 and 502 or 5001. So you can define that. So you can see that beyond this, if you go, then it will be your positive side. So then you can write this stability of region, but this you can further define also depending on your own calculations. Similarly, fourth order is there. Draw the graph, see how it is behaving, or put certain values of lambda h and see up to what it is going which way. Is that right?
Yes, sir.
Okay. So there are two ways. Now the another thing another form of E lambda h which we have written 1 plus lambda h by 2 divided by 1 minus lambda h by 2. This gives the higher order, second order method basically. You may come across later on. I'm not going to do at this stage. So we want magnitude of E lambda should be less than 1 for lambda h less than 0. For lambda less than 0, h is always positive, so lambda h will also be there. So we want that this quantity should be less than 1, or 1 plus lambda h by 2 should be less than 1 minus lambda h by 2. But lambda is less than 0, so this will become positive and this will become negative. So it is very obvious that it is true for all lambda. Is that right?
Yes, sir.
So for all lambda less than 0 means all things are happening, means your minus infinity to 0, the stability region is minus infinity to 0, full left half, right?
Yes, sir.
Is that right?
Yes, sir.
Okay. Now shall I move further? One or two more things are there, or you people are exhausted? Because today it was a theory, more theoretical part. Yes?
Exhausted, sir.
Exhausted? Okay, read this. Only one thing is left for complex lambda, right? We have seen for lambda greater than 0, lambda less than 0. How will we see for complex lambda? Then we'll see that whether real part of lambda is less than 0 or not, because complex number we cannot order it that it is less than 0 or greater than 0. So we see that real part of lambda once lambda is complex. So that I will do on the next term. So complete up to this. If you have doubt, you ask me. Whatever doubt you have does not matter. Adrija, Charvi,
Yes,
Jan,
Yes,
you
sir.
are there. Acha, Adrija, you are Adrija is speaking, I think. Adrija?
Yes, sir. I'm
Okay.
speaking.
So do the things. Wherever trouble is there, you ask me. Yes, Charvi, Jan, you are there. Charvi, Jan.
Yes, sir.
So if you go through the things, if you have any trouble, you can ask me. Yashvi Jain. Your friend has just logged in and left. Charvi.
Yes, sir.
There is some problem with the mic of Yashvi. She is replying in message. There's some
She
problem with
was saying something. So, okay, she has some net trouble.
Yash. She is sending messages here.
No, that
On
I have seen. But while teaching, it is difficult to see those chat messages. Because if I open chat box, then you people will see only that chat box rather than this one. So it is better if you can speak, or else you have any trouble today, so you can ask on the next one. There is no trouble at all. Okay, then for today I'm just closing at this stage. Go through the things carefully. Now theoretical and numerical, both the things are coming together, so you should be careful. And plenty of things are there, plenty of interesting things are there, rather I say. But the only thing is that you have to do the problems, more and more problems. I have already told how to make the problem. You can make your own problem with the exact solution, apply the method, any method which you wish to, and since you have the exact solution, you can compare with whether you are getting the close to the that or not. Right?
yes, sir.
Okay, so today I will just close at this stage. It was more than enough today. Yes. Anything? Snehbandhu, you are saying, or?
No, thank you, sir.
Okay, fine. Thank you.
Thank you, sir.